Picture this. Right now, as you're watching this video, the space between you and the Andromeda galaxy is growing. Not because anything is moving through space, but because space itself is stretching like a rubber band being pulled. And here's the part that should terrify you. We have absolutely no idea why. In 1998, two teams of astronomers made a discovery so shocking that when they first saw the data, they thought their equipment was broken. They were measuring distant supernova, trying to figure out how fast the universe's expansion was slowing down. Because of course it had to be slowing down, right? Gravity pulls everything together. The Big Bang gave everything an initial push outward, but gravity should be putting the brakes on that expansion. Except that's not what they found. The universe isn't slowing down, it's speeding up. The expansion of the universe is accelerating, and we don't know why. This discovery was so mind-breaking that Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize in Physics in 2011 for essentially telling us everything we thought we understood about the universe is wrong. They discovered that roughly 68% of the universe is made of something we've never detected, never seen, and can't explain. We just call it dark energy because we have no idea what else to call it. But here's what will really keep you up at night. The math that describes our expanding universe doesn't just fail at the edges of our understanding. It fails right at the foundation. When we try to measure how fast the universe is expanding using different methods, we get different answers. Not slightly different, significantly different. It's called the Hubble tension, and it suggests that either our measurements are catastrophically wrong, or the universe doesn't follow the same rules everywhere. Welcome to the most profound crisis in cosmology since Einstein. By the end of this video, you're going to understand why the universe's expansion might be the biggest mystery in all of science, and why solving it could change everything we think we know about reality itself. But before we dive into this cosmic rabbit hole, do me a favor, hit that like button and subscribe, because trust me, you're going to want to come back to this. And drop a comment telling me where in the world you're watching from, and what time it is for you right now. I want to know if you're having your morning coffee while contemplating the heat death of the universe, or if you're lying in bed at 2 a.m. having an existential crisis. Let's build a global community of people having their minds blown by the universe together. All right, let's start with what we think we know. The universe is expanding. What does that even mean? Most people imagine the Big Bang like an explosion in space, with galaxies flying outward from some central point like shrapnel from a bomb. But that's completely wrong, and understanding why it's wrong is the first step to understanding why this whole thing is so weird. Think of it like this. Imagine you're a bacteria living on the surface of a balloon. Your entire universe is the two-dimensional surface of that balloon. Now someone starts blowing up the balloon. From your perspective, every other bacteria around you starts moving away. The bacteria that were close to you move away slowly. The bacteria that were far away move away faster. But here's the critical part. None of the bacteria are actually moving across the surface of the balloon. The surface itself is stretching. That's what's happening to our universe. Space itself is expanding. Galaxies aren't moving through space away from each other. The space between them is growing. And this means something profound. There is no center to the expansion. Every point in space sees every other point moving away from it. You are at the center of the universe. So am I. So is someone in a galaxy 10 billion light years away. In 1929, Edwin Hubble made the observation that changed everything. He was working at the Mount Wilson Observatory in California, using what was then the world's largest telescope to study distant galaxies. He discovered that these galaxies were moving away from us, and the farther away they were, the faster they were receding. This relationship is now called Hubble's law, and it can be expressed simply. Velocity equals the Hubble constant times distance. The Hubble constant is supposed to tell us how fast the universe is expanding. It's measured in kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. The current best estimate puts the Hubble constant at about 67 to 73 kilometers per second per megaparsec, depending on how you measure it. And that, depending on how you measure it, part. That's where everything starts to fall apart. But let's not get ahead of ourselves. Let's talk about why we know the universe is expanding in the first place. When Hubble looked at distant galaxies, he noticed their light was shifted toward the red end of the spectrum. This is called redshift, and it's basically the Doppler effect for light. You know how an ambulance siren sounds higher pitched when it's coming toward you and lower pitched when it's moving away? Light does the same thing. When a galaxy is moving away from us, its light gets stretched out, shifting toward longer, redder wavelengths. The beautiful thing about this is that it gives us a cosmic speedometer. By measuring how much a galaxy's light is redshifted, we can calculate how fast it's moving away from us. And by measuring how far away it is, we can test Hubble's law. Everything should fit on a nice straight line, distance versus velocity. And it does, mostly. When we look at nearby galaxies and measure their distances using various methods, and we measure their redshifts, everything lines up beautifully. The universe is expanding exactly as we'd expect from general relativity and the Big Bang theory. But here's where things get weird. When we try to measure the rate of expansion using different methods, we get different answers. And I don't mean slightly different. I mean different enough that it can't be explained by measurement error. Let me tell you about the Hubble tension, because this is where cosmology goes from pretty weird to, are we living in a simulation that's glitching? There are basically two ways to measure how fast the universe is expanding. The first is the local method, where we look at relatively nearby objects in the universe and measure their distances and velocities directly. The second is the early universe method, where we look at light from the very early universe and work backward using our understanding of physics to calculate what the expansion rate should be today. Here's the problem. These two methods give us answers that differ by about 8 to 10%. That might not sound like much, but in cosmology, that's a 5 sigma discrepancy. In particle physics, 5 sigma is the gold standard for discovering something new. 5 sigma means there's only a 1 in 3.5 million chance this is a statistical fluke. Let me break down each method so you can see why this is so disturbing. The local method relies on something called the cosmic distance ladder. It's like a series of steps, where each step allows us to measure distances to more distant objects. The first step uses parallax, the same technique your brain uses to perceive depth. Hold your finger up and close one eye, then the other. Your finger appears to shift position relative to the background. By measuring how much nearby stars shift position as Earth orbits the Sun, we can calculate their distances. The second step uses Cepheid variable stars. These are stars that pulse in brightness with a regular period, and in 1908, Henrietta Swan Leavitt discovered something remarkable. There's a direct relationship between how long a Cepheid's period is and how bright it actually is. This means if you measure how long it takes a Cepheid to pulse, you know its true brightness. And if you know its true brightness and can measure its apparent brightness, you can calculate how far away it is. It's like knowing a light bulb is 100 watts and then figuring out how far away it is based on how bright it looks to you. Adam Rees and his team have used the Hubble Space Telescope to measure Cepheids in distant galaxies, allowing them to calibrate distances with unprecedented precision. Their latest measurements, published in 2022, give a Hubble constant of about 73 kilometers per second per megaparsec. Now let's talk about the early universe method. This uses the cosmic microwave background, or CMB. The CMB is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled, enough for atoms to form, and light could finally travel freely. The CMB has been mapped in exquisite detail by satellites like WMAP and Planck. and it shows us tiny temperature fluctuations that correspond to density variations in the early universe. What if I told you that this discrepancy might mean the universe doesn't have the same expansion rate everywhere, or that the laws of physics change over cosmic time, or that there's some form of energy or matter that we've completely missed? This is the Hubble tension, and it's not going away. In fact, as measurements have gotten more precise over the last decade, the tension has only gotten worse. We're now at the point where cosmologists are seriously considering that one of three things must be true. Either the local measurements are wrong in some subtle way we haven't figured out, or the early universe measurements are wrong in some subtle way we haven't figured out, or our entire understanding of how the universe works is fundamentally flawed. Remember how I mentioned that the universe's expansion is accelerating? Let's dive into why that's so completely insane. In 1998, Saul Perlmutter was leading the supernova cosmology project, and Brian Schmidt was leading the High-Z supernova search team. Both teams were doing the same thing, looking for Type Ia supernova in distant galaxies. These supernovae are special because they always explode with the same brightness, making them perfect standard candles for measuring cosmic distances. The teams were trying to measure how the universe's expansion was slowing down over time. See, after the Big Bang, everything got flung outward, but gravity should be pulling everything back together, gradually slowing the expansion. The question was, is there enough matter in the universe for gravity to eventually halt the expansion and pull everything back together in a big crunch? Or is there not enough matter, meaning the universe will expand forever? What they discovered instead was that the expansion isn't slowing down at all. It's speeding up. Distant supernovae were dimmer than they should be, which means they're farther away than they should be, which means the universe has expanded more than it should have over the last several billion years. Think of it like this. Imagine you throw a ball up in the air. You expect gravity to slow it down, right? Now imagine instead that the ball starts accelerating upward, moving faster and faster away from your hand. That's what the universe is doing. This should not be possible. There's no force we know of that could do this. Gravity only pulls, it never pushes. So what's causing the universe to accelerate? We don't know. We call it dark energy because we have literally no idea what it is. It's not a type of energy we've ever detected. It doesn't interact with light or matter in any way we can measure, except through its gravitational effect on the universe's expansion. And here's the truly mind-bending part. Dark energy makes up about 68% of all the energy in the universe. Dark matter, the mysterious stuff that holds galaxies together but doesn't emit light, makes up another 27%. Regular matter, everything we can see and touch, all the stars and planets and gas and dust, makes up only about 5% of the universe. We have no idea what 95% of the universe is made of. The leading explanation for dark energy is something called the cosmological constant. Einstein actually proposed this back in 1917, but he introduced it for the wrong reason. Einstein's equations of general relativity naturally predicted that the universe should be either expanding or contracting. But at the time, everyone thought the universe was static and eternal. So Einstein added a term to his equations, the cosmological constant, to counteract gravity and keep the universe still. When Hubble discovered the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder. But now it's back, resurrected as a possible explanation for dark energy. The cosmological constant represents the energy density of empty space itself. Quantum field theory predicts that even completely empty space isn't really empty. It's seething with virtual particles that pop in and out of existence. These quantum fluctuations should contribute energy to space, and this energy should have a repulsive gravitational effect. There's just one tiny problem. When physicists calculate how much energy quantum fluctuations should contribute, they get an answer that's about 10,120 times larger than the dark energy we observe. That's a 1 followed by 120 zeros. This is called the cosmological constant problem, and it's been called the worst prediction in the history of physics. So we're stuck. We can see dark energy's effects, but we can't explain where it comes from or why it has the value it does. And that value is absolutely critical. If dark energy were even slightly stronger, it would have torn the universe apart before galaxies could form. If it were even slightly weaker, gravity would have collapsed the universe back in on itself billions of years ago. We live in a universe that's perfectly balanced on a knife's edge, and we have no idea why. Here's where we need to talk about what happens when you push our equations to their limits. Because the expansion of the universe isn't just philosophically confusing, it's mathematically disturbing. Let me explain redshift in a bit more detail, because this is where things get truly weird. When we measure how far away a galaxy is, we use its redshift, denoted by the letter Z. A redshift of Z equals 1 means the wavelength of light has been stretched by a factor of 2. Z equals 2 means stretched by a factor of 3, and so on. Now here's the thing. As you look farther and farther out into space, you're also looking farther and farther back in time, because light takes time to travel. The farthest galaxies we can see have redshifts of about Z equals 11 or Z equals 12, meaning we're seeing them as they were about 13.4 billion years ago, only about 400 million years after the Big Bang. But there's a limit. In principle, if we could build a perfect telescope, the farthest thing we could ever see would have a redshift of about Z equals 1100. That's the cosmic microwave background, the light from when the universe was 380,000 years old. Before that, the universe was opaque, filled with a hot plasma that light couldn't travel through. But here's where the math gets disturbing. According to our equations, there are galaxies out there right now that we will never, ever be able to see. Not because they're too dim, but because the space between us and them is expanding faster than light can travel through it. Wait, you might be thinking, doesn't that violate relativity? Doesn't relativity say nothing can travel faster than light? No. Relativity says nothing can travel through space faster than light. But space itself can expand as fast as it wants. There's no speed limit on the expansion of space. This means there's a cosmic horizon, similar to the event horizon of a black hole. There are parts of the universe that are forever beyond our reach, not just practically, but fundamentally. The light from those regions will never reach us, no matter how long we wait. And because the expansion is accelerating, this horizon is actually shrinking. Galaxies that we can see today will eventually disappear beyond the cosmic horizon. In the far future, if the acceleration continues, observers in our galaxy will look out and see nothing but the local group of galaxies. The rest of the universe will have receded beyond the horizon. Future astronomers will look up at a dark sky and have no evidence that the universe is expanding, no evidence of the Big Bang, no evidence of all the things we've discovered. They'll be cosmically isolated, trapped in an island of light surrounded by darkness. But here's what really breaks the math. The acceleration means that in the far future, the universe will approach something called the Big Rip. If dark energy continues to dominate and its density remains constant or increases, the expansion will eventually become so violent that it tears apart everything. First, galaxy clusters will be torn apart, then galaxies, then solar systems, then planets, then atoms, then even the nuclei of atoms. The universe will be ripped to shreds by the accelerating expansion of space itself. The equations predict this happens in about 22 billion years if dark energy behaves a certain way. But here's the truly disturbing part. The equations don't just predict this, they require it. Unless something about dark energy changes, unless some new physics comes into play, the Big Rip is inevitable. And we have no idea why the universe would do this. What possible purpose could there be for a universe that tears itself apart? The math works, but it describes something so absurd that many physicists refuse to believe it's the real fate of the cosmos. Let me tell you about one of the most frustrating aspects of measuring the universe's expansion. It depends on how you measure it. And I don't just mean the Hubble tension. I mean that fundamentally, different methods of measuring distances in cosmology give you different answers about the structure and expansion of the universe. There's something called the cosmic distance ladder that I mentioned earlier, and each rung of that ladder has its own uncertainties and systematic errors. When you stack these rungs on top of each other, climbing from nearby stars to distant galaxies, those errors compound. But it's worse than that. Some methods of measuring distances don't use the distance ladder at all. They use completely independent techniques. And when you compare results from different techniques, they don't always agree. For example, there's a method called gravitational lensing. When light from a distant galaxy passes by a massive object like a cluster of galaxies, the gravity of that massive object bends the light, creating multiple distorted images of the background galaxy. By analyzing these images, you can calculate the masses involved and the distances to both the foreground and background objects. Then there's the Sun-Yov-Zeldovich effect, where light from the cosmic microwave background gets scattered by hot gas in galaxy clusters, creating a distinctive pattern that allows you to measure distances. There are Type Ia supernova, Cepheid variables, the Tully-Fisher relation for spiral galaxies, the fundamental plane for elliptical galaxies, surface brightness fluctuations, and several other methods. Each method has been carefully calibrated and tested, and they mostly agree with each other, but not perfectly. In 2019, a team led by Wendy Friedman used a method based on red giant stars to measure the Hubble constant. They got 69.8 kilometers per second per megaparsec, right in between the Planck measurement of 67 and the Cepheid-based measurement of 73. So is this the answer? Have we found the middle ground? No, because different teams using red giant stars get slightly different results depending on exactly how they calibrate their measurements. The uncertainty bands overlap, but the central values shift around. What if I told you that the problem might not be with our measurements at all, but with the assumption that the Hubble constant is actually constant? What if the expansion rate varies with direction? What if the universe is expanding faster in some directions than others? This would be absolutely revolutionary because it would violate the cosmological principle, one of the foundational assumptions of modern cosmology. The cosmological principle says that the universe is homogeneous and isotropic, meaning it looks the same everywhere and in all directions. If this principle is wrong, if the universe has a preferred direction or a center, then everything we've built our cosmology on collapses. There is some tantalizing evidence for this. Some studies have found that the expansion rate might vary slightly with direction, creating what's called a dipole in the Hubble constant. Other studies have found hints of large-scale structure in the universe that shouldn't exist according to the cosmological principle. There are enormous supervoids and superclusters that seem to violate the idea that matter is distributed evenly on large scales. But these results are controversial. For every study that finds an anomaly, there's another study that doesn't. The data is messy. The uncertainties are large, and it's easy to see patterns in noise if you look hard enough. Still, the fact that we're even considering these possibilities shows how desperate the situation has become. We're grasping at straws, trying to find any explanation that makes the numbers work. Here's where we need to talk about modified gravity theories, because if general relativity can't explain what we're seeing, maybe we need a new theory of gravity altogether. General relativity has been tested extensively, and it works incredibly well. It predicted the bending of light by the sun, confirmed by Arthur Eddington in 1919. It predicted gravitational time dilation, confirmed by countless experiments. It predicted gravitational waves, confirmed by LIGO in 2015. Every test we've thrown at general relativity, it has passed with flying colors. But here's the thing. we've only tested general relativity in relatively weak gravitational fields. The solar system, orbiting binary stars, even the extreme environment near black holes. We haven't tested it on the scale of the entire universe. What if general relativity is just an approximation that works well in certain regimes, but breaks down on cosmic scales? What if there are extra terms in Einstein's equations that only become important when you're dealing with billions of light years of space? One alternative is called modified Newtonian dynamics, or MOND. This theory proposes that Newton's law of gravity, and by extension, Einstein's general relativity, needs to be modified when gravitational accelerations are extremely small. MOND was originally proposed to explain the rotation curves of galaxies without invoking dark matter, but some versions of MOND might also affect cosmic expansion. Then there's FR gravity, where instead of the Einstein-Hilbert action that gives us general relativity, you use a more general function of the Ricci scalar curvature. This allows for all sorts of interesting possibilities, including modifications that could mimic dark energy. There's also something called scalar tensor theories, where gravity is mediated not just by the space-time metric, as in general relativity, but also by one or more scalar fields. These theories can produce accelerating expansion without dark energy. And then there are the really exotic proposals, theories with extra dimensions, where our universe is a three-dimensional brain floating in a higher dimensional space. Theories where the speed of light has changed over cosmic time. Theories where the universe is fundamentally discrete, rather than continuous, made up of tiny quantum units of space and time. But here's the problem with all these alternative theories. They have to reproduce all the successes of general relativity, while also explaining the things general relativity can't explain. That's a tall order. Most alternative theories end up being either too complicated, requiring lots of fine-tuned parameters, or making predictions that conflict with observations. Still, some physicists are convinced that the answer lies in modifying gravity. Because if dark energy really is the cosmological constant, and the cosmological constant really is 120 orders of magnitude smaller than quantum field theory predicts, then we have a fine-tuning problem so severe that it borders on the absurd. Think about what fine-tuning means in this context. It's like if you spun a roulette wheel with 10,120 numbers on it, and you needed to hit exactly the right number for the universe to exist, and somehow you did. That level of coincidence is so extreme that many physicists refuse to accept it. There must be some deeper explanation, some mechanism that sets the cosmological constant to exactly the value we observe. Or maybe we're just incredibly lucky. Maybe we live in a multiverse where different regions have different values of the cosmological constant, and we happen to exist in a region where it has the right value for stars and galaxies to form. This is called the anthropic principle, and it's deeply unsatisfying to many physicists because it gives up on finding a deeper explanation. It says the universe is the way it is because if it were any different, we wouldn't be here to observe it. But unsatisfying or not, it might be the truth. Let me tell you about one of the most fundamental problems in all of physics, because it directly impacts our understanding of the universe's expansion. We can't get quantum mechanics and general relativity to work together. Quantum mechanics describes the behavior of the very small, atoms, particles, fields. It's been tested to absurd levels of precision and has never failed. General relativity describes gravity and the behavior of spacetime on large scales. It too has passed every test we've given it. But when you try to combine them, the math explodes, literally. When you try to write down a quantum theory of gravity using the same techniques that work for other forces, you get infinities everywhere. The theory becomes non-renormalizable, which is physics speak for. This doesn't make any damn sense. Why does this matter for the expansion of the universe? Because the Big Bang was a quantum event. At the very earliest moments of the universe, when it was smaller than a proton, quantum effects dominated. But the universe was also incredibly dense, which means gravitational effects are also incredibly strong. You can't describe the Big Bang without a theory of quantum gravity, and we don't have one. String theory claims to be a theory of quantum gravity, but it's not clear if string theory is actually correct, and even if it is, we don't know how to extract predictions about the real universe from it. Loop quantum gravity is another approach, but it too has major unsolved problems. The upshot is that when cosmologists talk about the Big Bang and the early moments of the universe, they're extrapolating beyond the realm where their equations are valid. They're making educated guesses based on the assumption that somehow quantum mechanics and gravity play nice together in regimes we can't yet describe mathematically. This might seem like an abstract problem, but it has real implications. For instance, cosmic inflation, the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, requires physics beyond the standard model. The inflated field that drives inflation hasn't been detected, and we don't know what it is or why it exists. Inflation solves several problems in cosmology. It explains why the universe is so flat and uniform on large scales. It explains why we don't see magnetic monopoles or other exotic particles that should have been produced in the Big Bang. And it provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies. But inflation also makes predictions that seem designed specifically to be unfalsifiable. It predicts that we live in a multiverse, with countless bubble universes forming and inflating, each with potentially different laws of physics. We can't observe these other universes, so we can't test whether they exist. Some physicists love inflation. Others think it's the biggest cop-out in the history of science. The debate gets heated at conferences. But here's what's really disturbing. Inflation requires dark energy-like behavior in the early universe. During inflation, something caused space to expand exponentially fast, just like dark energy is causing accelerated expansion now. Are these two phenomena related? Is the dark energy we see today somehow left over from inflation? Nobody knows. And without a theory of quantum gravity, we can't even begin to answer these questions rigorously. All right, we're about halfway through, and I want to take a moment to step back from the equations and the measurements and talk about what all of this actually means. Because here's the thing, the expansion of the universe isn't just an abstract scientific problem. It fundamentally affects your place in reality. Every atom in your body was forged in the heart of a star billions of years ago. That star exploded in a supernova, scattering those atoms across space. They drifted through the cosmos, gradually coming together under gravity to form a new solar system, a new planet, and eventually, you. But here's what the accelerating expansion means. The raw materials that made you possible are becoming increasingly rare. As the universe expands and accelerates, star formation is slowing down. In the far future, perhaps 100 trillion years from now, the last stars will burn out. No new stars will form, because all the gas and dust will have been either locked up in dead stellar remnants or spread, so thin by the expansion that gravity can't pull it together anymore. The universe is dying. Slowly, inexorably, it's spreading itself out, cooling down, running out of the energy needed to create and sustain complexity. And you're living in a special time. Right now, in this era of cosmic history, the universe is still young enough and dense enough to be interesting. There are stars and planets and life. There's energy flowing, structure forming, possibilities being realized. But it won't last forever. The universe has an expiration date, and that date is determined by the expansion rate and dark energy. Think about what this means for the long-term future of intelligence in the universe. Could a civilization survive the heat death? Could they find a way to extract energy from the expansion itself? Could they escape into another universe somehow? These questions sound like science fiction, but they're the inevitable endpoint of taking cosmology seriously. If the universe is really expanding and accelerating the way we think it is, then every civilization that arises will eventually have to confront the same existential crisis. How do you survive when the universe itself is running down?